Lewis dot diagrams are a way to track the valence electrons. Each number above the column represents how many valence electrons every element in that family or group contains. For example, sodium receives 1 valence electron, which means 1 dot. However, nitrogen receives 5 because it's in the 5th column. However, nitrogen with a -3 charge means that it gains 3 electrons, so it has a full valence shell of 8. This brings us to elements' tendencies. The far left column, circled in black, generally bonds with the far purple column, circled next to the pink. These elements bond because one of them has 1 electron and the other has 7. So when they come together, they form a stable molecule. The far right column, circled in pink, does not generally bond because they have a full valence shell with 8 electrons. This then brings us to the irregular elements. Hydrogen only wants 2 valence electrons. Boron wants 6 valence electrons. Beryllium also only wants 2 valence electrons. Xenon and krypton, both noble gases, sometimes want 8, or they sometimes want 10 or 12 because of their d orbital. This means they can both contain more. Now we get to actually making the bonds. For H2O, hydrogen has 1 valence electron, but because there are 2 atoms of hydrogen, you get 2 valence electrons plus the 6 from oxygen for a total of 8 valence electrons to be shared between the 3 atoms. Hydrogen only needs 2 valence electrons, so the single bond between hydrogen and oxygen represents 2 valence electrons for each, representing oxygen having 2 from each bond, plus the 4 remaining valence electrons added to oxygen make up the full valence shell for oxygen, so all 3 atoms are stabilized with their full shells. Another example of a single bonded molecule is CCl4. First, you must add up the valence electrons from carbon for 4 and the valence electrons from Cl4 for a total of 28. That means there is a total of 32 electrons to be shared, and that carbon contains 4 single bonds connected to each chlorine for a total of 8 valence electrons for every atom in the molecule. Another type of bond is the double bond, representing a total of 4 electrons for each element it touches. As in the example CO2, there's a total of 16 electrons to be shared, but in order for each atom to get 8, there has to be a double bond between carbon and each oxygen for a total of 8 for every single atom. The final type of bond is a triple bond, representing a total of 6 electrons that are shared between the 2 different elements. This is represented through the bond of carbon and oxygen. Carbon with 4 valence electrons and oxygen with 6 make up a total with a triple bond for 8 for each atom, so their valence electrons are full and they are stable again. Another extremely important thing to remember is when you're dealing with a molecule with a charge, like NO3-. The significance of the minus is that the whole entire molecule gains 1 electron, for not a total of 23 electrons, but instead 24. When drawing these molecules out, you must remember to put them in brackets with the charge in the upper right corner outside of the brackets. If you do not do this, the question will be wrong. Then inside the brackets, you must draw the elements bonded together with the correct dots. The final part to Lewis structures is the subject of resonance structures. These are molecule drawings that can be drawn in multiple ways, which means the bonds can be placed in different places onto different atoms, as shown in the picture. It also requires that an arrow pointing in both directions is in between.